Which of the following represents the most stable conformation of 1-chloro-2-methyl-propane? And so we have the formula here, actually the condensed structure, looking down the C1 to C2 bond. So when we're drawing the most stable conformation of an alkane, we're going to represent it as a Newman projection, so we can look down that bond and see where our groups are oriented around each other in space. So let's kind of expand out this structure. So there's our carbon 1, and we've got a chlorine on it, as well as 2 hydrogens. And then our carbon 2 is this CH, and it has 2 methyl groups attached to it. So we have carbon 1, 2, and one of those carbon atoms would be 3. And so what we want to represent is this bond here, the bond between these 2 carbon atoms. And so whenever we're drawing the most stable conformation, the first thing that we want to think about is we want everything spread out as much as possible. So with a Newman projection, that means we are automatically going to be looking for a staggered conformation. So that is where all of your bonds are as spread apart as possible. And so you might see it oriented like that. And you should also recognize that if this gets flipped upside down, that those are equivalent. They are both staggered kind of frameworks. So what we're looking for then is the most stable conformation here. So if I were to start drawing this, I might draw a circle for the front carbon atom, and I'm going to automatically draw this framework. And I can put the chlorine on there and the hydrogens. And then I want to pay attention to where I'm putting the groups on the back carbon relative to this chlorine. So I want to try to spread things out as much as possible. So on that carbon 2, I'm going to have 1 hydrogen and 2 methyl groups. So what I don't want to do is put the 2 methyl groups here and here, because then I would have a lot of those 60-degree Gauss interactions. So I want to put 1 methyl group down here, and I'm going to be stuck with 1 methyl group that is next to the chlorine. So I'll put 1 here and say here, and that's to minimize those Gauss interactions. So when we're looking at our options, we might not find something that looks exactly like what we just drew. We're definitely going to eliminate these eclipsed conformations because those are definitely less stable. And so we've got 2 different staggered conformations to compare. And so we want to look at where these groups are relative to each other. So on this one, we've got one of these 60-degree Gauss interactions. And we were trying to avoid the structure where we had the other CH3 group here so that we would have 2 of those. So if we look at B and C, you might notice that here, or sorry, B and D, here you've got 2 of those 60-degree interactions. So that's what we were trying to avoid. So if we look at B, we've only got 1 of those, right? And we're also going to look at the relative position from this chlorine to the other CH3, and that is 180 degrees. That's as far apart as possible. So we want to make sure that we still have that same angle here between this carbon and this chlorine, and we do. So this should be our most stable staggered conformation that we can come up with for the 1-chloro-2-methyl propane.